So this is Iron Designer here, wanting to bring you a new video on construction management and developing and implementing Pert charts and CPM. For those of you that are not familiar with it, Pert stands for Program Evaluation Review Technique, developed by the United States Navy back in the 1950s. And CPM stands for Critical Path Method, also developed around the same time. And in this implementation and demonstration, we're going to use only Microsoft Excel to create and manage the models and do some statistical analysis. So what we're going to do in this lesson is I put together a brief lesson plan. What I'm not going to be talking about in this lesson plan are things like Slack in the schedule, because Slack, you can just learn about that once you've kind of mastered the critical path method and developing the Pert charts. So I think it's more important to do this work first, and if I get comments on the video, I can add on some methodologies for Slack. But for right now, we're just going to do these steps. I think it's going to be sufficient to get people started in construction management on Pert charts. And the first thing you need to do when you're assigned a project and you're working with a project manager, or you are the project manager, is putting together the list of tasks. And so you're going to have, some initial tasks that have to get done first, such as materials arriving at your construction site, or even if you're machining some parts, machining some goods, you need to start by listing those tasks first. A lot of other instructors relate it to a recipe where you get your ingredients first, you do your initial mixing or cutting or whatever, and then you begin the process of cooking according to your recipe. So item one is basically make a list of your tasks. Then number two, you're going to determine what the predecessors are. So some things need to be done before others, and some things need to get completed before other parts of the project can get going. And we call those the predecessors. The next thing you're going to want to do is assign durations to each task. So this is the most complicated part of doing a timeline chart or a Gantt chart, a Pert chart, or a CPM, is trying to figure out what the duration is for each task. And in the Pert chart, they break it down into three major categories. The first is the optimistic duration for the task, then the most likely, and then the pessimistic, which is the worst case duration. The next thing we need to do is compute the expected time. What that is, it's a formula, and I'll get into it when we get further into the spreadsheet, but it takes each of the three components and adds them together and divides and kind of gets some kind of average with the greatest weight on the most likely scenario. So that's computing the expected time. The next thing from statistics is to compute the variances, and that's basically a formula that you could put into the spreadsheet. The next thing is to compute the standard deviations from the variances, which is basically just the square root of the variances. We'll give you the standard deviations for each task. The next thing we're going to compute is the early start time and the early finish time for each task. And that's basically going in the direction from start to finish. The next category is the late starts and the late finishes. Those have to go backtracking from the end of the project, backtracking to the start of the project. And this is really where you can determine what some of your floats and slack times are. The next one is getting more information from the project manager or from your customers and doing a review and seeing if your original estimate approximation was accurate or is still doable. As you know, nowadays we have issues with supply chain and things, so that's something that you're going to be considering at this point. All of this is just basically a model, and your model has to be flexible enough to change and take in consideration changes as things go down from start to end. The next thing is computing the critical path. So once you've done all the steps above, you can begin to create a sketch, which is your Pert chart. And in the Pert chart, you can view the critical path items. From there, you're also going to take from that critical path, you're going to have certain tasks that are on the critical path, and you're going to look at those particular variances among all the variances. The next thing you're going to look at is computing the critical path standard deviations from the variances, and then you're going to compute the critical path z values, which is the normal distribution table, and I'll get into that later on in the video. You're going to use the z values to acquire the area in the normal distribution, which is going to give you the area under the curve. So in the step prior, you're just calculating the critical path z value, which is the number of standard deviations from the mean. At this point, you're going to acquire the area under the normal distribution to compute the percentages that are associated with those critical path standard deviations from the mean. And then later on, you're going to be completing the project manager's estimated completion dates, which has to do with what his estimate is based upon the critical path. And we're going to use the z values and the normal distribution to see what kind of probability and what percentage can we actually meet the date set by the project manager in the construction project. And then we're going to present our initial findings in a report summary, also part of the spreadsheet. And then we're going to make adjustments and repeat the process with any changes, or we're going to do the closeout analysis. So that's where we're going to go with the remainder of this video. So what I wanted to do here is go over the Pert table that I constructed in Excel. And as you can see, I'm just using a very old version of Excel, and there's nothing fancy in here. I think it's Microsoft 2000 or something. It's a very old copy. But I wanted to show you that a lot of this techniques and things in engineering and construction management, you really don't need a lot of high technology in order to get these things done. And for the most part, you really don't even need to purchase special Pert software or statistical analysis software. You can easily just look in a book, find the formulas, get a very good understanding of how to do it by hand. And once you can do it by hand, any spreadsheet can help you out. You don't need anything very high tech. But you do need to have a firm understanding of what you're doing and not just putting numbers on the table. So this is my Pert chart on the left. And in this particular project, I have 10 tasks. And that I'm just showing you this as my model. In reality, you might have 500 tasks or 700 tasks. But here, just so we can get started, I have 10 tasks. And I've just called my tasks A through J. Okay? The next of these columns, it talks about the predecessors. And we talked about that in the previous slide. And what it shows, what I've done is just made 4 columns here so that if I have a maximum up to 4 predecessors, I can list them. So A, B, and C do not have any predecessors. When you get to D, in order to start D, you have to finish A. That's why A is the predecessor of D. In order to get to E, you need to finish B and C. So you get B and C done. When they're both done, then you can start E. The same thing with F, G, they're the same, right? Now H, H only needs for C to get completed, okay? You never know just because they're labeled A, B, C, D. And letter C might actually finish quicker than B. We'll have to see what the times are over here. But there's a possibility in your project that C could complete before B. So here C needs to be done. And the next day H can begin right after C is done. Then you need G and H to be done before I. So if you think about it, B and C need to be done for G, and C needs to be done for H, and then G and H are the predecessors for I, and then likewise D and E are the predecessors for J, okay? So in this column here, all I'm talking about is that these have no predecessors because there's no letters here. This has 1 predecessor. These have 2. This has 1. This has 2. And this has 2. For those of you that are good with software like Python or C, you might be able to code this up as some kind of automated program, put this all in an array, possibly. So here, what I've done here, I've just written the predecessors in line. So here I've written them individually, and here I've just written them in line. So it'd be like B comma C, then C, G comma H, D comma E. They're just written in line, okay? The next step is to look backwards, okay? So now we're looking back. So if you were at D, your prior predecessor is A. So I just took this part of the chart and inverted it. So if you're at E, you look back, you needed B to get going, okay? And also at C, the next step is E. So if you're at E and you look back, you would go to C. If you're at J, you look back to D. J also looks back to E. Just like here, J needs D and E completed first. And over here at F, once you're at F, there is no other step. You reach the final stage. At G, you would look backwards. See if you're at G, you're the predecessor of I. So I looks back to G. H looks, I looks back to H. So here you have H. I looks back to H, okay? And then I, when you're at I and you completed I, you're at the end. And when you've completed J, you're also at the end. The next column here are now your estimate durations. Now these 3 columns are the most complicated in order to put together. You really need a lot of experience and working with the vendors and the suppliers and the stakeholders and the project managers in order to really get a good understanding of these. So if you have an optimistic duration, you could complete A in 10, okay? If you have most likely, like the average duration or your expectation would be 22, okay, to complete. Could be 22 hours, could be 22 days. Since we're doing construction management, we're measuring everything in days. Then you have the pessimistic duration is the same as the most likely, so that's that. B is going to be, say, 20 optimistically, and you go on down the line. You go down the line for each one, okay? For computing the expected time, I'll show you the formula in the next slide. The expected time is basically the optimistic time plus 4 times the most likely time plus the pessimistic time, and you'll get the expected time. So if I clicked on this cell, you can see it's the expected, the optimistic duration plus 4 times the most likely duration and plus the pessimistic duration. That sum divided by 6, okay? So you can see that it's heavily weighing on the most likely time. It's trying to get 4 times this plus that plus this. Now you have 6 factors because it's 1 plus 4 plus 1 is 6. So it's dividing that by 6. So the expected time is kind of like an average, okay? With heavily weighing on the most likely time. The variance is just a value computed. Now for right now, just ignore that I've colored these red. Just ignore that for now. We'll get into that in a minute. The variance is now taking the pessimistic duration minus the optimistic duration and dividing that by 6. So again, this is just statistical analysis. It's just statistical definition of how they want to define the variance, okay? So it's taking the extremes, dividing it by 6, and then squaring it, okay? Now the standard deviation is just taking the variance and taking the square root of the variance, okay? The units here column is just so that if I have a value in the expected time column and the value is just anything greater than 0, even if it's just a 1, then I put a 1 in here. This gives me a validation that I have at least some time, at least a value of 1 in the expected time column. So this just gives me a validation of that. The next things that we need to look at are the early start, the early finish, the late start, and the late finish. What happens here in the early, the 2 early columns, is that those are computed looking forward from start to end. And we'll get into that when we look at the Pert chart. The late start and the late finish is where you backtrack and you look backwards from the end going back to the start. And this is where you're going to find out what your slack times and your float times are as you go backwards through the Pert chart. So that's that. The reason I highlighted these is because these highlights are the actual critical path values from the CPM, and this right here is the longest duration. This is the critical path. So in order for the project to get complete, it needs to be done in 43 days. but we'll see later on that the probability of it getting done in 43 days is low because you've got variances in your times. And also the reason why I highlighted it in the variance column is because it has to do with the statistical analysis in one of the next slides. What I'm showing here is a graph, a bar chart of the optimistics, the likely, and the pessimistics. So you can see just graphically and visually what the spread is. In some cases, like task 1, which is right here, task 1, you can see that there's not any variation between the likely and the pessimistic. So you can only take advantage of it if you get it done in the optimistic time. Here, say in task 2, task B, there's no advantage to any of them. So they're all the same number. You have the same value. For some reason, that's just what it is. Somebody, gave you these estimated times. No matter what you do, it's always going to be 20, all right? So maybe that's the delivery time of something to arrive, that you cannot speed it up, you cannot slow it down. It's just a fixed duration. So you can look through all your bar charts. You can see some are vastly different. Maybe something is shipping from overseas, and if you get it expedited, you can have it quickly. If you miss that expedited service, it takes longer. If you have trouble with supply chain and you miss expedited service, then you have a very big issue here with the pessimistic time frame. What I'm showing here in the expected times, because with a pie chart, you can see here this column. I've made a pie chart out of this column. You can see the percentages of what each of the tasks is using in the pie chart. So everything adds up to 100. You can see that 1 and 2 are almost 15% of your project. And you can see that in the expected time, they are 20. And that's the highest percentages in the pie chart. I just did this just to show it to you visually. But you can see that these are the most encumbering tasks in your project. You then have like a 15, a 14, an 18. So you can see that 18 is number 9. So you look here at number 9, it's 14% of your project. You look here at the 15, which is number 4. Number 4 is 12% of your project. So these, appear like they might get involved in some of your more critical paths of completion. Here are your standard deviations. I just wanted to take a look at that, which is this column here. You can see that some standard deviations are very high, and number 9 has a very high standard deviation and a very high variance. And you look at number 9 on the pie chart, on the column chart, and you can see from the pie chart that the standard deviation is affecting, say, 23% of the standard deviations of the rest of them. And that's absolutely true when you look at what could happen in your pessimistic duration. Same thing if you look at number 4, which is here, it also has a high variance. Number 9 had a high variance, but it's not on the critical path. But it could affect 22% from your standard deviations. And you can look at the bar chart and you can see that, yes, that is true. That's why I wanted to show you these bar graphs. And we're going to take a look at the Pert chart in the next slide. So I just wanted to jump into the Z table chart really quick to show you that it's just basically what you would get out of a textbook. So if you look in any textbook, they're going to give you something like a a Z table, which is like a normal distribution table, and you can find them in statistics books, project management books, probably some appendix in math books. And what it is, really quick, is it's basically some columns, and these are in hundredths. So you have like from 0. So if it was exactly this number, it would be the 0 column. If you have 100th, 200th, up to say the 900th column. So say you have a number like 0.7. This right here is 0.7. If it's just 0.70, and I know this is kind of small, but it doesn't matter. You can just look in a Z table and follow along. If you look at the 0.7 row in the positive side of the Z table, not the negative side, we're just looking in the positive side, because we're hoping for greater percentages than 50%. That's why we're in the positive side of the Z table. Then if you look in the 0.7 row, and it's just 0.7000, usually goes out to like 5 decimal places, 6 decimal places, then what it tells you is that you have, I think it says like 0.7804, 0.75804 would be at exactly 0.7 on the Z table, and that's the number there. What that means is that to the left of this normal distribution, you would have slightly greater than 75% of the normal distribution table to the left. So you're encompassing like 75% of the probabilities and the data to the left of the chart on the normal distribution. So in this case, if you want to get very exact, you'd be at 75.8, okay? If you're down here, say at 1.3, and you're at 1.36, so I clicked on the 1.3 row, and I'm on the 6th column, so you're at 1.36, then it's, in the Z table, it's telling you 0.91309, which now, if you have a standard deviation on the positive side of the table of 1.36, then you're covering 91.3% of all the probabilities are to the left of where you're at. So if you have like a 1.36, that means you have a 91.3% chance that the probability you're looking for and in the Z table is there. So that means statistically you have a 91.3% chance of success. Now these things go all the way down to something like nearly 4 standard deviations. So if you're down here at 3.99, and I go in the last column, which is a 9, then now you're here at 99.997%. That's how much of the normal distribution curve you have to your left. So you've got almost a perfect chance of success, you know, with 5 decimal places. You're at 99.997% ability to have the data you're looking for is within your normal distribution. What I'm doing here, and I'll get to it in the next slide, is that my statistics slide is sending over the breakdown of, say, in this case, the standard deviation was 1.21. And what I wanted to do is break it down, because the 1.2 is going to give me the row that I'm on, if I'm using VLOOKUP. And then I wanted to truncate off the next digit, because that's how the digits are broken down. There's no sub digits broken down. You could interpolate if you want But, for construction management, I mean, even if you're within 0.5% accuracy, I think that's okay because, you know, are you going to work half a day or something on a construction site? The answer is no. You're going to work in the unit of days. So the 1 is telling me that I'm in column 1. So here's column 1. So my standard deviation is 1.21. So my row is 1.2, and I highlighted it here for you. 1.2, and I'm in column 1, even though the standard deviation was 1.21. I'm trying to show you the breakdown. You go down there, and you click on that, and you get 88.686%. Here I've truncated it down to just 3 digits, 3 significant digits. And in percentage terms, your probability is 88.7% that you're going to have that data point within your statistical analysis, which I think is very good. So in construction, if this were to say you drop this down and you said, well, you have an 88% chance of getting the project done within 45 days, according to the Z table and according to your Pert chart, if you remember that, then if these numbers are accurate and we're just basing it on these estimated values, then in your Z table chart, you're coming with at least 88%. You're good to go. So we're going to talk more about the statistics in the next slide, and just stay tuned for that. Okay, so I try to make my videos as exciting as possible, but I know that math and statistics, are kind of frowned upon, but they're exciting to me. So I love numbers, and you need to have basically a table like this to start to organize your numbers a little bit better so that you can really understand what numbers are coming in as input and what numbers are going out as output, and ultimately how you're going to make your determination. Because if you need to give a presentation, say to a stakeholder, a vice president, a CEO, a project manager, the president of the company, or you're doing training exercise for more junior construction managers or junior project managers, they're going to want to understand your entire thinking process. Where did all your numbers come from? And how did you, most importantly, how did you come up with the conclusions that you came up with? So that's why this slide right here is very important, and I'll just try to go through it quickly, and then we're going to go and look at the Pert chart. And then lastly, we're going to look at the final slide, which is the output report, the summary. And then you should be experts in Pert charts and CPM at that point. So what we have here in the very first row here, now you remember we already did the CPM. We computed, we're just saying we computed the critical path, and we'll get to that. We'll get to the Pert chart in just a moment. But let's say for now, we know the length of the critical path. Remember, in the Pert chart, it was 43 days. But let's say that based on that, we've spoken with the project manager. We've shown him our Z table. We told him that, right now, we're only computing a 1.21 standard deviation. We showed him the Z table, and he says, well, okay, you know what? I'll just get it done in 50 days, all right? And he's kind of quick to answer you, and you're the project analyst. So you put in 50 days in there, and this is going to be the input that ultimately leads us to the 88%, okay? And we tell them the critical path is 43. The CPM computed input expected times summation was 43 days. He says, good, just give me another week of padding. I'll get it done in 50 days. All right. Now we've seen that the summation of the durations is different, but many of them are in parallel, so it's not really a direct summation. So in order to be 95% confident, we would need the CPM to be 48 days, okay, for a 95% confidence level. But right now, what we've done is we've taken the data that we have. Remember, it's just a model and it's flexible. So we've taken our model and we're computing the calculated standard deviation from the critical path variances only. So we have D13, which is this value here. This is the computed summation of the critical path variances from the Pert chart. So if you look at the Pert table, remember I highlighted these. So if you take 25 plus 4 plus 4, it's you get 29 plus 4 is 33, right? 29 plus 4 is 33. So this is where the 33 comes from. Now, this value is the Z value, basically. We take that variance, which is the standard deviation, we take that calculated standard deviation from the critical path variances, and we take the square root of that number. So when you take the Z value, what you're going to do is you're going to take the days that the project manager has, you know, estimated for you, right? He's not doing an analysis. He's just saying, well, if you give me a critical path of 43 days, add on another week and give me 50 days. He's assuming that that's enough time. So you take the difference of the 50 and the 43 and you divide that by the calculated standard deviation from the critical path variances number. And again, that number is the square root of the computed variance summation. Remember, I need to just remind you, 25 plus 4 is 29 plus 4 is 33. Okay? 33. You take the square root of that. Okay? Then you take the difference between the project manager's estimate and the critical path, okay, and you divide it by the calculated standard deviation from the critical path variances, okay, and you come up with your Z value of 1.21. I just lopped off the 9, so I'm only looking at a 1.21, and this is the lookup value that is in the Z table. If you remember, it's 1.2, and then I'm using the 1 as my column because you remember those are the hundredths and these are the tenths of the standard deviation, the rows. So these are the rows here and these are the columns. So it's important. That's how you're determining this number. That's how you're coming in on the row and you're stopping on the column. You're getting your percentage number, the 88.7. Okay, it's right here. If you can see, if I expand that, you can see there's the number from the Z table chart. It's just pulling the number from the table. All I did is just trunked it down, and then I converted it to a percent. And back in the statistics, so that's that. This is just the chopping up of that number and dropping the 9, because 1 is like 2. If you want to be more accurate and round up, you can do that in your chart. I decided to truncate it down because it's going to give me a lower a lower percentage. So as you move to the left, you're getting worse and worse percentages of confidence, right? So if I was here and I had gone up, it would say 88.8%. But because I rounded down, I'm taking a more conservative approach to 88.7, okay? That's why I did that. I'm here just visually checking the column. I'm just doing like a round down of the value. You can see the formula up here. And there's the number from the Z table chart. And there's what I tell the project manager. I say, if you do it in 50 days, even though the critical path is 43, but you have to remember we have very high variance values. And that's why we report back to the PM 88.7. So we'll get back into the rest of the slides in just a minute. So I just wanted to bring you back to this statistics table for just a minute. So we were talking about the 50 days from the PM, and I didn't really talk to you about these numbers here or these. So the 66, the 128, and the 202 is just the straight summations from the Pert table. So if you go here and you just add these up, it would reach 66. So right there, 66, 128, and 202. I just wanted to kind of go back to that for a second. So here, what you want to do, if your critical path is, say, 43, then what you need to do is look at the project manager's estimate, and you want to try to widen the gap between these in order to raise this number up. So if you put it on 66, say, and you change it to exactly 66, see, you're at 100% done, because that means that you're no longer working in parallel the way the Pert table was telling you that you have predecessors and all that. You're just doing every task in order all the way down, and you're totally ignoring predecessors and trying to get things done in parallel. That's why if you put it in your optimistic number, and anything equal to your optimistic number or higher is always going to give you a 100% guarantee that you're always done on time. So that's why that's why having a model like this that you can tinker around with is so important. And, you know, instead of doing it on paper, but now once you've modeled it, you can tinker with it. That's what I was saying. If you're a Python developer or a C, C++, Java developer, JavaScript, code this in and you'll be able to tinker with this a lot easier even than in Excel. So here, if I go back to the 50, you see it drops back down to the 88%. Anything above that, if it's 55 days that the PM can get it done in, and again, I don't know if he can get it done in that time frame. Maybe there's a time constraint. But now see, it jumped up to 98%. If the PM can go to 60 days, you're at 99.8. But if you went down to 42 days, the PM said, well, I got to cut a day off the CPM, then you see everything goes negative. And you're not going to be able to do these lookup values. You're going to be losing days. So that's why the chart that we use, the Z table chart, is a 50% chart. See, when I click on that uppermost cell at 00, it tells you 50%. So the best you can achieve is 50%. See how everything kind of like crashed? But if you go back and you change this back to the 50, see, everything goes back to normal, and we're back where our estimate is. So I just wanted to go and talk about those columns. This here is just playing around with the Z values, and this is at, say, to be 95%, you want a 95, you'd put in here like 48, I think. No. So that formula came out of one of the PM books. Maybe it should be something like higher, like 53 to get to there. So there's some error in the formula that I got out of the textbook. But let's finally get into the Pert chart. And this is the slide for the Pert chart so we can kind of visualize our path. So quickly, just going back to the Pert table. Remember, we've got 10 tasks, and some have predecessors, and there might be some parallel paths to get this thing done. And we're not just doing it on 66, which was the, if we just did every single task sequentially and we totally forgot about trying to work in parallel, we're going to get done in 66 days. But the PM says no. I'll do it in 50, and we give him an 88.7% chance of completing on time. Again, remember, in the Pert chart, we have variances. We have very high variances. You remember these standard deviations are just basically a reflection of variance, and you remember some of these could cause us problems, like this pessimistic value, this pessimistic value. And the problem is with number 9 is that these predecessors could cause us some issues. G and H, which was 7 and 8. So here 7 is not really an issue causer, but 8 could be a big cause to issue, and it could really cause 9 to stumble and fall. So in the Pert chart, we have a starting point, and all the early start, late start, everything is at 0, okay? And I basically created this kind of 9 cells in here because it contains all the information we need. So you go to the legend here, you have early start, early finish, you have the time, the duration, that's just in the middle. This is our name of our task, ABC, the late start and the late finish. And if you remember, ABC was ABC, they have no predecessors. So they kick off immediately, all in parallel. They kick off at the same moment that the project starts, okay? They all kicked off together. The colors, don't worry too much about the colors for right now. Obviously, this is going to be the critical path, the purple one. The other colors are just to distinguish between the arrows, so not everything overlaps. Quickly, I just want to show you that F, once you've completed F, that goes straight to end. It doesn't mean the project is done, but F doesn't have any further tasks after F. Okay, nothing depends on F. And we can confirm that by looking here. Once you see F, you don't see F in any subsequent rows. There's no letter F anymore. So F goes to the end, okay? Now, early start on A, early start on B, early start on C, they're all at 0. They're at the moment of start. The duration of A is 20, B is 20, and C is 10. That confirms these. So you have the durations of A is 10, 20, and 4, right? So let's take a look at that. I'm sorry, when you go here into the expected times. So 20, 20, 10, right here, 20, 20, 10, okay? So let's look at the chart. So you have 20, 20, and 10, okay? So the early finish went from the moment I start A with the duration, an expected time of 20, because we got to go with the TEs, And I'll note that here, that the early finish is 20. We can't really look at the late start, late finishes right now till we go completely through the Pert chart, and then we work backwards to calculate these bottom numbers, the LS and the LFs. They get calculated by subtracting the TE values from the CPM. So here D has to follow A, and the soonest D can start is when A finishes. So A finishes on 20, D starts on 20. It has a duration of 15. So D has a TE of 15, right? And you add these together. So the early finish, the soonest D can finish, is when A ends, D starts. It has a TE. This is the sum. You go down to the next one, say E. E has a predecessor of B. B finishes on 20, plus his TE is 10. His early finish is 30. And we could just keep going like that. So now you get to J. J starts when D finishes, has a duration of 8, gets to 43. And then J gives its 43 number to the end. But we have to look at I. So I, if you follow the path, no matter what the predecessors are and all that, 24 is the accumulation of all his predecessors' longest durations, right? Plus his own TE gives us a 42. So the larger the two values goes into the end. So that's how you get the CPM value. So wanting to compute the LS, you go to the 43 of the end, you put that into both LFs for each of the kind of terminate task. Then you begin subtracting. So 43 minus 8, which is the TE of J, is 35. Okay. And then here, minus 18 is 25. So since these, you see the two arrows, these are the two predecessors of I, just like we have in our Pert table. So I has GH. So you go back to the Pert chart. So we're looking at 25. We put 25 in each of the LFs, okay? And we subtract their TEs. We get here a 21 and a 14, okay? Now on the LS's, you have to put the lower values going back. So if you have two competing values to C, then C has to take the lowest value of everybody that's a dependent on C. So here it would have been 25, 29, 21, and 14. You have to put the lowest value. So the lowest value is 14. You subtract the TE of C, and the LS, the late start for C, is 4, which means that C doesn't have to start on 0. C could start on day 4. And then if you backtrack for B, B also has a late start of 1. So it could start the day after A, and it wouldn't affect the CPM. That's what you're trying to determine, is anything going to affect the CPM. So like here, 43 minus 14 is 29, right? And then from B also has to put in the lowest LF of its it's the predecessor of E, F, and G, and 21, 29, 25 we put the 21 in there because it's the lowest, and we subtract its TE, and we get a 1. So the late start on B is a 1. If you guys comment below, I will make a video using this same chart. I'll just add on things like slack and float, but I'm not going to discuss it in this video. And I just wanted to now get over to the output. So all these values here are just cells within the spreadsheet, okay? So if you're a Python programmer, these would be variables populating these cells, and you'd report this out in a report format. And what we have here, just as a brief report, I mean, the report could go on as long as your corporation wants it to be explanatory. There are 10 tasks in the model. We got that from the Pert Table Q29. You remember when I added these up, and then you go down here, and that's the 10 right there. That's Q29, okay? So everything in here, the max predecessors, is again coming from here. So this is just max. See the max of this column. And anyways, here are the summations. Here's the estimate from the project manager. Here's the percent probability of completion. Here's the critical path. And then this is the, in percentage format, the project manager's probability to complete. You'll see that if I go back to statistics and I change this, say, to 55, and we go back to output, see it automatically did the update. So this is a way to play what if and play with the model and see what you could get from doing the modeling. So this is IronDesigner. I hope this was very helpful to you. If it was, please share, like, subscribe, and comment. And let me know if you want me to add on slack and float. And I will do that. And if you have any other video requests you'd like, please put that in all caps in your comments. And I am now out.